Today we want to talk about a new kind of function. Specifically, they are called vector fields. So here's what's new about this new kind of function. We're going to apply these functions to R2 and R3. I suppose we could apply these to the real numbers, but that would look really weird. Normally, what we've been dealing with so far are scalar functions. Up to now, we've been using scalar functions. What I mean is that the output is a scalar. We put in either a real number or an ordered pair or an ordered triple, and out pops a scalar. So y equals f of x, or z equals f of x, y, or w equals f of x, y, z. We input a real number, an ordered pair, an ordered triple, and out pops a scalar. The thing here is that the output is a scalar. Y, z, and w, the output is always a scalar. Our function has been a map from the real numbers to the real numbers. For here, if f of x, y is equal to z, our function maps R2 to the real numbers. For f of x, y, and z, our function has as a domain R3 and as a codomain the real numbers. The output is just a scalar. The codomain is R. So what we want to do now is change the codomain, change the output from a scalar to a vector. That's what's going on in a vector field. So the output is going to be a vector in R2 or a vector in R3. We're going to use some different notation to distinguish our vector fields from just regular old functions. This is not necessary. It's going to be a local thing that we do. It's very common, but we're going to use different names for things. For example, here's a vector field. Capital F at xy is y times I plus x squared times j. We can see that the input is going to be an ordered pair xy. So the domain is R2. But our output is yi plus x squared j. Our output is a vector. So our codomain is also R2. But our output is not just a point in R2, our output is a vector R2. So to each point in the plane, we are assigning a vector, not just a value. To each point in the plane, we are assigning a vector. To each point in R2, we are assigning a vector instead of a scalar. Before, we were just mapping a scalar, each point in R2 to a particular scalar. Now we are mapping each point in R2 to a vector. So when we plug in 0, 0 to this particular vector field, we get the 0 vector, not just 0 the number, 0 the vector. If we plug in the point 1, 0, we get the point 0i plus 1 squared j, so 1j. So our graphs are going to look very different. Our graphs are going to look very different because at each point, we're not just plotting a value. We're not just plotting a single point. We're plotting a vector. So if I start trying to draw this, which is always a mistake, and yet I always try to do it. At the point 0, 0, I plot the vector, I plot the vector 0. At the point 1, 0, I plot the vector 0, 1. At the point 2, 0, I plot the vector 0, 4. At the point 0, 3, I plot the point vector 0, 9. If I plot some values on the other side, if I plot the point, let's say, -1, 0, y is still 0. So I get the vector 0, 1 again. This is just the vector field evaluated at these 7 points. if we move to a different point, we'll get a different vector. So for example, if I plot the point or the vector 0, 1, this case, y is 1 and x is 0. So I get the point, I get the vector 1, 0. At the point 0, 2, I get the vector 2, 0. At the point 0, 3, I get the vector 3, 0. This is all just because of the way that the vector field is defined. This time, if I go into the negatives, if I go to the negative y-axis, f of 0, negative 1 will be negative 1i plus 0j. None of this is very surprising. All the x's are going to give us positive values, so all these vectors should go up in the x direction. But in the y direction, we see when x is positive, we go to the right, and when x is negative, we go to the left. Let's plot some other points. So if I pick a point, let's say the point 1, negative 1. Let's see, try to get an idea of what's going on down here in the fourth quadrant. At point 1, negative 1, we have negative 1i plus 1 squared j. So negative 1, 1. So down here we'll have at the point negative 1 or 1, negative 1, we'll go negative 1 in the x direction and 1 in the y direction. At the point 1, negative 2, my vector will be negative 2 in the I direction and 1 in the j direction. So we'll go negative 2 in the I direction, 1 in the j direction. And if I go down to negative 1, negative 3, we'll go negative 3 in the I direction, 1 in the j direction. So we can see kind of the vectors are all horizontal on the y-axis. And then on this line right here, we can see they're kind of like spinning up to when we get to the x-axis. So it's like at an angle, a negative 1/3, negative 1/2 slope, negative 1 slope, vertical slope. Let's see what happens after that by looking at the points 1, 1. We'll have y is 1 in the I direction and x is 1 squared in the j direction. So now it's like at this point, we have flipped around and now we're going in the other direction. Then at point 1, 2, two in the I direction and still 1 in the j direction. So now I have a slope of 1/2. And then at 3, 1, we'll have a slope of 1/3. And it gets messy because my vectors are all overlapping. And if we want an idea about more points, we just keep plotting points to try to get an idea. So let's see, -1, -1, 1. I wanted something on this side too. So y is 1 and x is -1. So the idea is that at every point, we have a vector. Now let's draw R3 and X, Y, and Z and try to plot vectors in that. I'm just kidding. That would be a disaster. It's already getting messy, and I've only plotted a very small number of points, and we've already got some overlap. And I've already had to cut the size of the vectors in half, roughly, to get the idea that we're going for. But we can imagine what happens if we can take this same concept to R3. So here we are standing in the room. At every point in the room, we can imagine a vector, vectors all over the place. And we can think of that as maybe the wind currents, as the wind blows through the room. Gosh, I wonder what made me think of that. As the weather huffs and puffs and tries to blow the school down outside. We could think of a vector field in R2 as the flow along the surface of the water. This would be really weird for water to flow this way, but we can imagine water things floating on the surface of the water. Here are the two things that we want to think about in vector field, with a vector field. Let's suppose that we have a vector field. What can we do to imagine it? And what will we do when we think of it that way? So we want to think of a vector field in R2. I want you to imagine, let's say, the surface of the water. So here's how we can note a vector field. Notice that the capital F naming the vector field has a vector symbol over it. So I'll write a typing, this would be a bold F to indicate that that capital F is a vector. Notice that F1 and F2, those are both scalar functions because each one of those, F1 and F2, is just is a scalar function telling us the components. So the components have scalar functions. Capital F is a vector field. or a vector valued function, but f1 and f2 are scalar functions for the components. So those two are scalar functions. We plug in x and y to f1 of xy, and we get a scalar. And that tells us what the x or the I component is. F2 is a scalar function. We plug in a point x, y, we get a scalar. That's the j component of vector field F. It's great that we keep using F for this because now we have to distinguish between lowercase f, uppercase F, and vector field F. I should name one of these vectors lowercase vector F, and then we really have a mess. It'll be awesome. So let's suppose we have a vector. We want to imagine this. We can imagine this as the flow of water on the surface of the water. So imagine the flow of water on the surface of the water. At every point on the surface of the water is flowing around somewhere. That's how we can imagine the vector field in R2. Just imagine R2 as the surface of water, and the vector field is showing you the current. That's the word I was trying to think of. Imagine the current on the surface of the water. At every point, we can figure out which direction the water is flowing, where the current is flowing, and we put an arrow indicating the direction. If the water is flowing fast in one direction, then we'll have a long arrow. If the water is kind of slowly moving in one direction, then we'll have a short arrow. So I could draw the vector field for a river. So here we would see a river where all the water is flowing in the same direction, but we have faster currents over here on this down here and slower currents along this part. So the water is flowing in the same direction, but maybe these slower ones indicate that there's the deeper part of the river. So it's going slower. We have a slow current up here. And then faster currents down here at the bottom. Maybe there's some kind of obstruction. So around here, we'd see the water trying to break around the obstruction. I'm not a fluid dynamics guy, so don't at me. But if we look at all those points, we might see the water flowing around. I know I made it too round for the water to just flow around. I didn't put like, just don't at me. Zoom in more and you can see that I drew really tiny little eddy currents so that they're all swirling around. So, I mean, if we zoomed in closer, there would be some pointing back this way because I drew it so round. As soon as I start drawing the obstruction, I go, I should draw like an airfoil so that it will flow evenly off there. I go, nah, make a circle. And my weak memory of fluid dynamics is like, oh, dumbass mathematicians, man. So if we have a vector field in R3, we're going to do the same thing, but since water would tend to fall, we'll just imagine the air current flowing around. So if we have a vector field in R3, we can imagine the air current around the room. Imagine the air current flowing around the room. For a function, a vector field R in R2, we want to imagine the air current flowing around the room. That's how we can imagine our vector fields in R2 and R3. That's where we're always going to start. Water flowing on a surface, air flowing around the room. What kind of things are we going to do? Now that we've imagined this function, it's really hard to picture. It's not like drawing the graph of a function where we imagine a one-dimensional curve in three-dimensional space or a two-dimensional surface in three-dimensional space. Because there's vectors everywhere. So it's not like one line we can draw or one surface that we can draw. It's everywhere vectors. So we got to think about what we're going to do with this information. There are a couple of things that we want to think about with this information. We want to think about the flow of the vector field. Some things to think about. Think about the flow of the vector field. If we just take a leaf and drop it on the water, what path would that leaf take as it just followed the vector field around? So think of a path. There's a leaf on the water. We just watch how it sails around. It'll follow some path. It just goes with the currents. Or if we take, I need something lighter, like a feather, and let it go in the room. Better yet, Well, I'd rather use a leaf, but I don't know if I have enough wind. We can imagine a particle of dust as it just follows the air current around the room. That will be the flow of the vector field. It'll be a bunch of different paths, depending on where we start. There'll be a bunch of different paths that that piece of dust might follow. So there's dust in the wind. The dust and the leaf just follow the path of the vector given by the vector field. Dust in the Wind, it's a Kansas song. I think is it Kansas? As soon as I say things about music, I immediately think I'm wrong. Do the song Dust in the Wind. You don't need Spotify, you just need the internet and you have it. Sorry, I'm being snotty with Siri. That's not nice. See, now I have to know. There was a time where I just didn't have to know things. Kansas. So the dust and the leaf follow a path given by the vector field. That's one of the things that we're going to think about. Some other things we're going to think about. Imagine if we want to carve our own path through the vector field. How does the vector field help or hinder us as we go along? How much are we going with the flow? How much are we going against the flow? So another thing that we might want to think of is carving our own path through the vector field. So this is what we'll think about tomorrow. We'll think about the flow of the vector field. We'll think about carving our own path through the vector field, and then some other vector field things. But right now, you're about to walk out into a very good example of a vector field as the wind just kind of slams into you. Take a piece of dust and let it go in the wind to see what kind of path it follows, so you can see the flow of the vector field when you're walking in. Imagine as you're walking into this vector field, you're carving a path through the vector field. How much is it helping you, hurting you to walk into the wind going that way? How much is it helping you to walk with the wind going out to the parking? That's it for today. I will see you all on tomorrow, and we will pretty much finish the thinking behind vector calculus. Everybody have a good day. Thanks for playing. You too.